Okay, here I've got another topic from Chapter 2 in the Optics chapter, and this is the topic of diffraction. I've given you a couple of homework problems that include diffraction calculations, so I'll give you here a couple slides that introduce the subject and get you up and going on those problems. Important stuff because, as I'll explain at the end of the video here, it relates very closely to coupling of light into fiber interfaces. Okay, so we've talked about the wave nature of light. What that means is that we have to account for different parts of a wavefront which superimpose with each other to create the new wavefront forward in time. So we're going to be using the superposition principle where either constructive or destructive interference could occur. And what the result of this is that we get diffraction patterns. Diffraction patterns show up as fringes. You may have seen photographs of this or be familiar with the phenomenon, I hope. And for our purposes, what we're interested in is the spot size, that is the non-zero spot size, in the case where light is focused by a lens. So what I'm going to do is I'll start by taking a picture, by looking at the case where we have collimated light being brought to a focus by a lens, something like this. And in the ray picture, in the ray picture, this spot, this is the focal length here, and there's the focal point of that lens. In the ray picture, this this point of focus really is a point, and we have an infinitely focused beam of light, but that doesn't happen in real life. in particular, we call the non-zero place, the region of the focus, the spot, and we say that the spot size is non-zero or greater than zero. And in order to quantify that spot there where the light has come to a focus, we're going to look at the intensity profile of a light beam. And so what we're going to do is we're going to slice this beam like this, and we'll take as a function of, let's call this the y-axis, as a function of y here, and then we'll set y equal to 0 on the optic axis here, and we'll make the assumption that this is a uniform beam of a certain width, in which case the beam profile looks like this. It's non-zero, and this is intensity of the beam, optical intensity, as a function of that spatial dimension. And so this is a uniform beam of light. So this is a uniform beam. And if this lens has diameter d, then the extent of this uniform beam in this picture is it just fills the lens, so it's d over 2 to minus d over 2. Okay, so now what we'll do is we'll take this idea where we've quantified the shape, the profile of a beam. So there's the profile of that beam, and what we'll do is we'll take two cases. We'll consider, first of all, this same case we just considered, the uniform beam brought to a focus. And what we'll do is we'll draw our lens here, and we'll bring this beam to a focus. So this uniform beam is brought to a focus here, let's say. But what we're going to find is that, if I can draw it correctly, that we have a little bit of a spot size there. Okay, and the slice of this beam profile through that spot is going to look as follows. And here I'm going to plot it as a function of the radial coordinate r. Okay, because it is cylindrically symmetric, and so I'm going to plot this intensity profile like this. And this is the appearance of fringes, because we have a very bright spot in the center where the intensity is large, and it dies off, but then there's little bumps out here which essentially create fringes. And so the appearance of this spot looks something like a bright central spot with fringes. I can't draw them fuzzy the way they really are, but fringes getting of decreasing magnitude going out from the radial direction. And it turns out that the full width of this central spot, so let me sort of make this a little bit more formal here and go ahead and draw this central spot. The full width of that central spot is denoted D, and it's 2.44 lambda f over big D, which is the diameter of the lens. So we'll say that this is diameter D. Okay, and I hope you can read that. And the things to note here are that it is, so this is the diameter of the central ring. Let's call this of the central ring. Okay, and so the first thing to notice is that it's proportional to the wavelength, lambda. You scale the wavelength and all the other physical phenomena scale is proportional to the focal length and is inversely proportional to the diameter d. As we increase the focal length, the spot size increases, and finally as we decrease the diameter, the spot size increases. And so that combination f over d essentially is measuring the angle of these rays coming in. Okay, and so basically a larger lens is going to give a smaller focused spot size than a smaller lens, and this is something we're familiar with when you do photography. Larger lenses give you better, sharper images. And in particular, notice that you can't have little d, that is the diameter of the central ring, going to 0. Okay. Next, we'll look at the case of a Gaussian beam, and a Gaussian beam, I can't really draw the profile of it, but very often we go ahead and just draw the convergence of a Gaussian beam like this, where there's a small waist to the beam at the focal point. And what happens here is that our intensity profile is now a Gaussian, I of r, and I'm going to go ahead and put r equals 0 in the middle of the plot this time and draw the full Gaussian here. Okay, so I of r is something like I naught e to the minus 2r squared over w squared, where w is characterizes the width of this, and at that point the intensity has gone to 1 over e squared of the intensity at the peak. Okay, so w is called the spot size of the Gaussian beam. And it turns out that a Gaussian beam in produces a Gaussian beam out. Okay, so if we have a Gaussian beam as input, of width W, then the output will also be a Gaussian beam with width W naught is equal to lambda F over pi W. So this is a nice situation, and the first thing to notice is that the width of the output beam is inversely proportional to the width of the input beam. We have the same lambda F in the numerator that we had here, and in fact these two are relatively consistent with one another as far as their spot sizes go. This is important because the output of laser diodes can often be represented quite well with a Gaussian beam profile. Also, the lowest order mode in a step index optical fiber also has a mode shape which is well approximated by a Gaussian beam. And in coupling to fibers, what we're going to be interested in is matching the beam profile at the input of the fiber to the profile of the mode that we want to be propagating in that fiber. And so this is a very important case that we'll consider. And that's it for this presentation. Thanks.